Welcome to Flow and Energy Losses. First, let me start by going over the objectives of today's topics. If you remember from last time in previous lectures, I described the laminar flow and the turbulent flow. I also stated the relationship between different parameters that are used to calculate the Reynolds number, the importance of Reynolds number, application of Reynolds number, identify the limiting values. Remember 2000, 4000, those two numbers. If the flow, if the Reynolds number is less than 2000, that's a laminar flow. If it's above 4000, it's the turbulent flow. And if it's between 2000 to 4000, that is the transition zone for the flow. So we have covered all that and also went over an example. Today I'm going to start by talking about Darcy's equation. I'm going to introduce Darcy's equation to you, and we're going to take a look at how we can apply that equation to compute the energy losses due to friction. And we're going to take a look at both cases of laminar and the turbulent flow. Then I'm going to take a look at the other equations that we use for computing the energy loss due to friction in laminar flow. Then we would talk about the friction factor as we apply it in Darcy's equation. We also talk about Moody's diagram and how we can use that as a means of combining both Reynolds number and the relative roughness to look at the fluid flow. Then we're going to compute the friction factor using equations developed by these two scientists. Then we're going to compute the energy loss due to friction for fluid in circular pipes and so on. So it's pretty involved. At last, we're going to take a look at the Hazen-Williams equation. These are all basic but very important equations and applications, and that we need to know before we can claim that we pretty much took a fluid mechanics course. So these are all important topics, and they are pretty applied. Standard applications in the industry they are numerous. So let me take a look at Darcy's equation. Remember when we went over the general energy equation, we talk about the pressure, we talk about the other parameters that were involved here. We also talk about, we use a reference point and we measure the height of the point in which we can actually try to measure the pressure or what have you, with respect to that point, like a reference point, and we measure that. We call it Z sub 1 and Z sub 2. So the general energy equation is as shown here. There are the term H sub L here. H sub L in this equation is defined as the energy loss from the system. As you can see, originally we had the left-hand side of the equation. The equation didn't have any of these terms, H sub A, H sub R, and H sub L. Those that would actually doesn't take any energy out of the system, and actually it helps the system by adding more energy to it. Those terms are shown as positive here. For example, H sub A. Those that would cause the energy to be reduced, then those terms are shown by minus number and they're subtracted. So if you want to go from point 1 with pressure P1 with the fluid velocity at that point as V sub 1 and the point itself, Z sub 1, that's the location of the point that we discussed previously. If you want to go from point P1 to point P2, of course, in the process, there would be some energy loss, and there's also some energy that could be gained. So one component here that we are going to concentrate is H sub L. H sub L is the energy loss from the system due to friction in the flowing fluid. The fluid itself has friction as it flows, especially in the case that we looked at it as layer by layer. There is friction between these layers, and as such, as the flow moves, it loses some energy, and that is accounted here in this equation by H sub L, and it shows with a negative sign because it is a loss, not a gain. How can we calculate H sub L? We are going to use Darcy's equation. Remember that most of these equations are named after people that are that originally developed the mathematical formulas and mathematics behind it. Some of them they're being hydrologists, some being from different types of engineering field, and some of them pretty much the scientists that contributed to the field of fluid mechanics. One of the most important equations that are pretty much well known to anybody that works with fluid is the Darcy's equation. Darcy's equation is an equation in which we can measure the energy loss due to the friction in the flowing fluid. The terms that appear in this equation as such must be measured, and we must be able to have some kind of a numerical some kind of a value associated, a numerical value associated with these parameters. In this equation, H sub L, again, it's called energy loss due to friction. F is the friction factor. Again, this is another dimensionless number. The length of the flow stream is shown here as L. D itself, since we're talking about closed circular conduits, we are talking about pipes, and that is the diameter of the pipe, and the V is the velocity of flow. Of course, we use an average velocity of flow because the velocity of the flow, even at a cross section, it might be varied. If it is a more smooth surface, that variation would be less, but if it's more rough surface within the pipe itself, then the average velocity, the fluctuation in the average velocity would be in the velocity would be higher, and we need to take the average value for that. So Darcy's equation is used to calculate the energy loss due to friction in round pipes. Let me get my camera back here. There we go. Okay, so another relationship is known by Hagen-Poiseuille equation. Hagen-Poiseuille equation. Again, these are the name of the people that originally developed these equations. And that equation describes the relationship between certain measurable parameters of the flow system. As the flow within the system have been studied, these like a parametric study, these parameters have been identified, and they were actually verified by experiment. Of course, there's mathematical equation behind it. Engineering, we can't just use something for the heck of it because it's just the way it is. We try to describe whether it's a motion of a fluid, flow of the fluid, whether it's anything that's related to engineering and mechanics. We try to formulate it because engineering is a consistent field. It's an accurate field. That's how engineers are distinguished from other people. Good engineers, they are accurate people, and in most cases that also applies to their other aspects of life. So the parameters that are involved here is the viscosity, as shown here. It's the specific weight. There are some geometric parameters here. One is the L, the length of the flow, and also the diameter of the round conduit pipelines, pipe diameter. And of course, the average velocity So this pretty much covers it all. And of course, one thing that we know is that for a laminar flow, because the flow is so smooth, the pressure is low, the Reynolds number is low. As such, the flow of the energy loss in laminar flow, it is independent of the condition of the pipe surface. As we're increasing the pressure, as we're increasing the velocity of the flow, and as we go beyond the Reynolds number of 4,000, then the condition of the pipe surface comes in, and that's going to play a key role in that process. So viscous friction losses within the fluid governs the magnitude of the energy loss. Let's continue with our examination of the Hagen-Poiseuille equation and Darcy's equation and see if we can relate the two. This equation again is valid for Reynolds number less than 2000, and we are going to equate Darcy's equation with the Hagen-Poiseuille equation. They can be equated, and if because they're both determine the H sub L, they're used to calculate the loss of the energy due to the loss of energy H sub L due to the friction, so they could be equated. So we equate these equations, we do algebraic manipulation, we play around with these parameters, and we derive F here. Note that this symbol is called eta, it's a Greek symbol, and gamma, which you guys are pretty familiar with it by now, it's shown here. The rest are not Greek. L is L is the length, V is the velocity, and D is the diameter of the circular pipe. So we equate these equations, and we come up with an equation for F as shown here, and we know that rho would be gamma divided by G, so we basically replace gamma divided by G and by rho. Also, we previously defined what Reynolds number is, and then we're going to substitute that in there to develop some kind of a relationship between the Reynolds number and the friction loss. As such, we would develop this simple equation equating the friction loss by an inverse of the Reynolds number multiplied by 64. That is 1 divided by n sub r multiplied by 64, which is nothing but 64 divided by n sub r, which is the Reynolds number. So the energy loss due to friction in laminar flow can be calculated from both the equations of the Hagen-Poiseuille equation, H sub L that's shown here, or it could be calculated from Darcy's equation as shown down here. Of course, in the Darcy's equation, there is a dimensionless friction factor. It's called F, and that is shown down here, and it is calculated basically by dividing n sub r. Moving on, let's take a look at an example problem. In this problem, we try to determine the energy loss if the fluid itself is a glycerin at 25 degrees Celsius. Remember, the temperature is going to give us the temperature is very important because it would determine the viscosity of the fluid and so on. There's a 30-meter pipe line that this fluid needs to go through. The diameter of the pipe is 150 millimeter, and the average velocity is 4 meters per second. So let's try to solve this problem. First, We need to determine if the flow is laminar or turbulent. As such, we need to calculate the Reynolds number. And of course, we need to have the properties of the glycerin at 25 degrees Celsius. Remember that we have 4 parameters here. Let's see how many of them are given. V is given and D is given. And we need to calculate rho according to the fluid and its temperature. So it's glycerin at 25 degrees Celsius. That's 1,258 kilometer per cubic meter. What we used here, I'm sure you guys are familiar with that symbol by now. Try to think what that symbol was before I move on. Okay, well, I'm going to mention that later throughout the lecture. Just take a guess and we move on. Anyways, so that's a good test for you to remember some of these Greek symbols. This is rho, of course, pretty much well known, but it's the other parameter that I'm just wondering if you guys know what that is. Have you guessed it? Okay, it's actually eta, right? Right? Eta, E-T-A. So that's what this symbol is. So moving on, after we have that little exercise. So we're going to plug in all these numbers in the equation that we use to calculate Reynolds number, and it turned out to be that Reynolds number is 786. Let's take a look at this 786. What does that tell us? Remember 2,000, 4,000? And 786 is less than 2,000, okay? And that means that the flow is a laminar flow, right? Great. Moving on, we are going to use the equations that we already developed. First, we are going to use the Darcy's equation, okay? Remember, we already calculated Reynolds number, 786. We already have this formula in order to calculate the friction factor, a dimensionless number. We divide Reynolds number, well, we divide 64 by the Reynolds number, or we multiply the inverse of the Reynolds number we calculated here by 64. That would be 0.081. H sub L is then from this point on nothing but to plug in the numbers that we already have. H sub L would be 13.2 meter. Again, we want to make sure that we get the units correctly for the quantities that doesn't have any dimension. We don't worry about those, but in this case, we express the units in SI, and of course, the resulting H sub L energy loss would be a meter or Newton meter per meter. What it really tells us is that when we express it in Newton meter per Newton, it means that for every Newton of glycerin, there would be a 13.2 meter of energy loss along the pipe with a length of 30 meter. Okay, so now let's move on and take a look at a turbulent flow. With turbulent flow, because of the complications that are involved with the flow, remember here we are dealing with a high velocity flow, we are dealing with mixing, we are dealing with pretty much a wild action of the fluid. In that case, it is more difficult to predict that. On top of that, the surface of the pipeline itself, the internal surface of the pipeline, any roughness that we have associated with that is going to also affect the turbulent flow. So it is more complicated to deal with a turbulent flow than with a laminar flow. Turbulent is more unpredictable. It is something that is not as easy understood as the laminar flow. So for this case, we basically rely on the experimental data to determine the value of F. Of course, we can determine the value of F, the dimensionless friction factor. That would provide us with some basics, but again, in this case, the velocity, the Reynolds number is over 4,000, so we have difficulty in many cases to apply that. So this dimensionless F in this case, again, we need to bring in two main parameters here. One is Reynolds number, the other one is the relative roughness of the pipe. So the relative roughness is the ratio of the pipe diameter to the average pipe wall roughness. It is shown by the Greek letter epsilon. We use this epsilon also in statics and in materials to relate that to the strain. But in this case, we use that, the Greek letter epsilon, to show the wall roughness. And of course, the wall roughness would be variable along the length of the pipe. In that case, where do we measure the diameter, and then how do we measure the radius? What is it that we use to actually measure the epsilon? Usually it's the largest in the roughness, and it's not easy to measure that. In many cases, we rely on experience, and we rely on the manufacturer's data that is provided to us. So friction loss in a turbulent flow is a good idea to use the table that's given here. Roughness for both in meter and in feet is given here. Remember, these numbers are very small. You may think that they really do not have much effect because they're so small, but trust me, they do, because even these small numbers would going to have effect on the flow. As you are dealing with solving more problems, you realize that every little bit of every small number, no matter how small, would have the effect. As you can see, for glass, we are dealing with 3 times 10 to the minus 7. The number is much smaller than when we are dealing with riveted steel or with concrete, even well-made concrete. In that case, 3 times 10 to the minus 7 would be the roughness, or epsilon in meter. And down here, for well-made concrete, it's going to be 1.2 times 10 to the minus 4. So you can see the variation as we are going down, the numbers are getting larger. So again, these are average values. They are for new clean pipe. There will be variations when we do the calculations for the older pipes. It's always a good idea not to go beyond the service life of the pipe, but in some cases, some of these pipes are buried, and it is not as easy as we think it is to replace these pipes. One of the major reasons is the economic factors. It's going to cost money. If it's run by the government, they come and go, priorities shift, and so on and so forth. Sometimes there are also political issues behind that. We try to stay away with those in this course, and we try to concentrate on our discussion. So the ratio of capital D divided by epsilon is very important to realize. Of course, if we are dealing with glass, it's smooth, then that ratio approaches infinity, and we should be okay. Of course, as we're going down this table, then that ratio would become larger and larger, and it becomes very difficult to deal with that. Well, actually, it becomes as the epsilon becomes larger and larger, then d over e would become smaller and smaller. And as we are increasing epsilon, if the smaller the epsilon, the better it is, and we don't really need to worry about that ratio. So other types of pipes, the standard steel pipe, both schedule 40 and 80, and welded steel tubing. The roughness value is the one that is listed, and we use those. And of course, it is a good idea to always call the manufacturers of the pipes and ask them for all these values. And they have all these values for us while they're testing their pipes, and before it goes to the production, there's some industry standards that they need to follow to ensure proper manufacturing techniques and proper data to be sent to the consumers and engineers. Let me take a look at the Moody diagram at this stage. It is the diagram itself is not Moody. It is named after the person that developed this diagram. His name was L.F. Moody, and this is one of the most widely used diagrams in fluid mechanics. We use that for evaluating the friction factor. And in the diagram itself, which I'm going to go over shortly, the friction factor F is plotted versus the Reynolds number N sub R with a series of parametric curves related to the relative roughness that I just mentioned, the ratio of the diameter of the pipe divided by the epsilon, D divided by epsilon. These curves, again, are generated by Dr. Moody. Both F and N sub R are plotted in logarithmic scales for values between 4,000 and 2,000. For Reynolds number values between 2,000 and 4,000. We don't have any curve for that, and that's a critical zone. Remember, we went over this, and it is not possible to predict the type of flow, but for other types, it's shown on the Moody diagram. Let me take a look at the Moody diagram. On the x-axis of this diagram, at the bottom, these are Reynolds numbers. Again, this is a logarithmic scale, so make a note of that. On the left-hand side, y-axis, the friction factor F is shown. On the right-hand side, y-axis, a relative roughness D divided by epsilon is shown. As you can see, there are regions of complete turbulence that's shown up here. It goes from this dashed line up here all the way to the right side of the curve. Anything that is to the right of the dashed line, it is the completely turbulence flow, and all these numbers would fall on the right side of the dashed line. For smooth pipes with a given Reynolds number, as you can see, we can pretty much come up with a friction factor and relative roughness. As you know, first we calculate the Reynolds number, then we continue that. It's going to hit the diagram at some point, and then we continue the line to the right to calculate the relative roughness, and we continue the line to the left to calculate the friction factor. An example is, for example, if you have a Reynolds number that falls here, you draw a straight line. Of course, this is not straight, but a straight line that goes through the curve. Let me try this again. Maybe I can do it better. There we go. So this is supposed to be a straight line. As you can see, this straight line would actually cut these lines at some point, the intersection of this line and all these curves that are shown here. Of course, if I continue this, depending on what the relative roughness, the relative roughness and friction factor, of course, that can be calculated as you can see here. So, for example, relative roughness of 500 is this line. When we continue this relative roughness of 500, we continue that. Remember, that is not the epsilon itself, but it's the ratio of d divided by epsilon. So in that case, we continue this line, and you can see that beyond some point it's going to go and reach the laminar flow. So if you continue 500, at some point it's going to coincide with this line, and that would be this point here, and then you need to find that intersection and continue a horizontal line, and that would be the friction factor. If also the friction factor is given, you can do it in the inverse method and use the relative roughness of the pipe or even the Reynolds number if you know the type of the flow that is involved in this case. So a very useful and important diagram. This line here is a straight line. This is for the laminar flow, and for that laminar flow, the F would be 64 divided by n sub r. So we never violate that rule. If the flow is laminar, of course, the F, or the friction factor in this case, the dimensional number would be simply 65 divided by Reynolds number that we calculate. So please keep that in mind. So let me take a closer look at the Moody diagram, some of the important observation. Of course, if we are given a Reynolds number as the relative roughness d divided by epsilon is increased, the friction factor decreases. And very important for us to know that, because this would be some kind of a guide to help us with actually confirming that we are in the right direction when we read these numbers. For a given relative roughness of d divided by epsilon, the friction factor F decreases as we are increasing the Reynolds number until the zone to the right of that dashed line, that is the zone of complete turbulence. Within the zone of complete turbulence, then the Reynolds number has no effect on the friction factor. So we're really beyond anything that we can measure in this case as far as the Reynolds number is concerned. As the relative roughness increases, again, d divided by epsilon, make sure you use this terminology that is called relative roughness, because it is relative to the dimension of the diameter, the inside diameter of the pipe, and so that is d divided by epsilon. As the relative roughness increases, then the value of the Reynolds number at which the zone of complete turbulence begins also increases. A closer look at Reynolds number, for example, is given here. This is the same graph for a Reynolds number of 4,000 is shown down here. This is the limit. Remember, the lower bound for the turbulence, the upper bound for the transition zone. 4,000. The lower bound of the Reynolds number for this transition zone is 2,000. Of course, between the two, one could be considered lower bound, one could be considered upper bound. So depending on what we're looking at, the lower bound and upper bound would become relative. As you can see, to the right of Reynolds number of 4,000, it's turbulent. To the left of it is laminar. And As you can see again here, the lowest possible friction factor in this case for really an arbitrary Reynolds number in turbulent flow is indicated by the smooth pipes line, as you can see it. Again, we need to have a good understanding of Moody's diagram, and I hope with more practice you would get a better handle of that. Some more accurate number. These are important numbers because they are routinely used in fluid mechanics for Reynolds number of 6700. The roughness, the relative ratio D divided by epsilon would be 150, and F would be 0.0430. As we are increasing, going down here, okay, then we are increasing. In this case, it's really not higher than 2000 and 2000, but it is 733. So there is some increase from this number to this number down here, and F would be 0.0223 and so on. So this is good for practice. Use these numbers, this table, to check your ability, to see if you can read these numbers off of the Moody diagram. Okay? Okay. All right, so let's move on and take a look at applications of Moody diagram. So let's take a look at another way that we can approximate and use it as direct calculation of the values of the friction factor for a turbulent flow, and that is called, this equation is developed by Swamy and Jain, and that is the Swamy and Jain equation, and that is commonly referred to. Again, in this equation, this equation it allows the direct calculation of F in cases that calculation would be possible. So that's another extension of that. So again, there's some error associated with this. Experimental data shows that this is within a good range, plus or minus 1%, within the range of relative roughness, from 100 to 1 times 10 to a million, and for Reynolds number from 5 to 10 to the power 3 to 1 10 to the power 8. So 5 times 10 to the power 3 to 10 to the power 8. This is pretty much the entire turbulent zone of the Moody diagram. So in order to calculate the value of friction factor F when the Reynolds number and relative roughness are known, we use F as 64 divided by N sub R for laminar flow, and we use the equations that I just showed you for turbulent flow. All the parameters are already defined. Note that this is the log as shown here, and this formula is a good approximation. Okay. So let's take a look at the famous Hazen-Williams formula for water flow. We've already seen Darcy's equation and how we can use that to calculate energy loss due to friction. This is for Newtonian fluids. As we are approaching the higher velocity and turbulent flow, then these equations they may not be applied the way we like. Another alternative approach that is used in many cases. For example, in the flow of water in pipeline systems, which I've used many times, is the Hazen-Williams formula. This is, again, among those most popular formulas for designing a water system. It is limited to the typical applications for pipes with diameters larger than 2 but smaller than 6 feet. Those are 2 inches to 6 feet. That's a good range of many typical pipelines. For sewage pipelines, we do the D-load calculation, which is beyond the scope of our course for those large diameter sewage pipelines. Just for you to know, we cannot have velocities greater than 10 foot per second. Again, those are typical values that we use for designing a system, a flow of water in pipeline systems. So there are some limitations, but it is pretty common for the most of the pipelines that we design and use. Of course, the temperature, this is developed for the benchmark temperature of 60 degrees Fahrenheit, and if this is used in temperatures somewhat close to 60, it works. If it is too high and too high above 60 and too far below 60, we are going to have results in the equation. The U.S. customary unit system of Hazen-Williams formula is shown here in this equation. We need to define all the parameters. V is the average velocity of flow, foot per second. C sub h is the Hazen-Williams coefficient. That is a dimensionless number. R, not to be confused with RE, which was also another term that we use to define Reynolds number. This R here is the hydraulic radius of a flow conduit. That is in foot. S is the ratio of H sub L divided by L, and that is simply tells us the energy loss per unit length of the conduit. That's foot per foot. And now the question is, how do we calculate R, the hydraulic radius of flow conduits for within the range of application? Remember, we use 2 inches to 6 foot. That's the diameter of our pipe. In that case, R could be taken as hydraulic radius as D and divided by 4 for circular pipes for our applications. So C sub H is one of the parameters in this equation, was a coefficient. It depends only on the inside condition, surface condition of the pipe. Some typical values of C sub H are given here for different types of pipes that we can use in our calculations. That was for U.S. customary units. For SI units, because of all these factors that are involved, again, we have the same type of equation, except we have S in this case as a parameter. S is H sub L divided by L. Again, it's energy loss per length of conduit. And the volume flow rate that we introduced in previous lectures, Q A times V, also applies in this case. Knowing A, knowing V, we can easily calculate the volume flow rate Q. There are also other types of Hazen-Williams formulas that are used, other forms. Again, it's important to know what the application of Hazen-Williams formula is it is used to determine the required size of the pipe to carry a given flow rate while limiting the energy loss to some specified value. We don't want too much of the energy loss. It is also used to determine the energy loss for a certain flow rate, knowing the length and the size of the pipeline. So other forms are also given here. You can study those on your own. There is a nomograph for solving the Hazen-Williams formula, and that it is important to note here. As you can see, the volume, there are four lines that are shown here, four vertical lines that are showing. The one to the right is the velocity. And this is good for if we know two of the parameters, we are going to draw a straight line through those 2 points and continue that, and we determine the other values from the Hazen-Williams nomograph. For example, if we know velocity at 2.5, for example, that's this point, and if I know the volume flow rate, desired volume flow rate, let's say this is it, then I can connect 0.03 cubic meter per second to 2.5 meter per second, and I can read the diameter of the pipe, in this case in inches, and I can also determine the head loss in this case. And there's one example here that is shown. So again, this nomograph is used if we know two parameters. It is also possible to use it in one parameter, but that would be really an approximation. If, for example, you have a 6-inch schedule 40 steel pipe, CS is 100, and for example, S is 20, and I want to see what would be the allowable velocity. I can pretty much use that graph. In that case, it's going to be 4.3. This is the line that is shown here in terms of dash line. Practice with it, do your best, and let me know if you have any questions, and if you run into any type of a problem through the course. Post it on the discussion board, email me to the course website as well. Some points here is noteworthy, and that is the velocity, Q sub C, D sub C, and S sub C. One is the velocity, one is the volume of flow rate, pipe diameter, and head loss. Look at the relationship between these as they relate to C sub H. Again, practice with this graph and let me know if you have any questions. That pretty much brings me to the end of this recorded lecture. It is rather long, but you guys can always pause and digest pieces at a time. As always, send your questions to me via the course website. Thank you.